Hello, my name is David Reiter, and I'm going to be highlighting some of the findings from our most recent paper published in Magnetic Resonance in Medicine entitled Anomalous T2 Relaxation in Normal and Degraded Cartilage. Quantitative MRI is increasingly used as a sensitive imaging modality for diagnosis of osteoarthritis. In particular, monoexponential T2 relaxation times have been associated with a degree of cartilage degradation. Although monoexponential T2 shows sensitivity to cartilage disease, it exhibits a limited degree of specificity to pathology. For example, T2 can be modulated by other factors such as exercise, age, gender, and hydration, to name a few. Furthermore, monoexponential T2 relaxation times are not specific to matrix components, showing correlations with both collagen content and proteoglycan content. Non-monoexponential T2 relaxation has been observed in cartilage, and multi-exponential relaxation models have demonstrated improvements in specificity to matrix macromolecules, with T2 component fractions corresponding to proteoglycan content in normal and degraded cartilage. However, multi-exponential analysis places high demands on the MR acquisition in terms of the signal-to-noise ratio and sampling rate of the decay, which limits its applicability, particularly for imaging studies of cartilage, which is a thin anisotropic tissue with relatively short T2s. Recently, we described two alternative anomalous T2 models, the stretch-Mittag-Leffler and the stretch-exponential models, for describing relaxation in cartilage. Unlike the multi-exponential model, which assumes to some extent discrete compartments with distinct relaxation times, these two models can incorporate broad distributions of relaxation times and can describe processes influenced by multiple length scales and diffusive transport of water through a heterogeneous medium that can modulate T2, which is perhaps more suitable for describing relaxation in a porous fluid-filled tissue like cartilage. This work's objective was to examine anomalous T2 models of relaxation in cartilage pragmatically with the goal of improving the early detection of osteoarthritis. Accordingly, to be diagnostically relevant, these models should be able to first of all capture anomalous relaxation decay features. Secondly, they should be able to provide parameters specific to the individual matrix components. And third, they should be measurable under clinical imaging conditions. This means that whatever model we want to apply must be able to produce accurate and reproducible parameters under imaging conditions with limited signal-to-noise ratio and low temporal sampling resolution and signal decay. We examined four models. The mono-exponential model shown here is used as a point of reference with which to compare the anomalous models with. This model has T2 as a parameter of interest. The stretch-Mittag-Leffler model shown here has an additional fitting parameter alpha, which appears as an exponent of the argument of time. The Mittag-Leffler function, symbolized by capital E sub alpha here, is a generalization of the exponential function. It is defined using the power series with the Greek character gamma representing the gamma function. For an alpha value of 1, the Mittag-Leffler function is equivalent to the exponential function. The stretch exponential model shows a similar form to the mono-exponential, but with the argument of time raised to the power of alpha. Similar to the stretch Mittag-Leffler, for an alpha value of 1, the stretch exponential function is equivalent to the mono-exponential function. Finally, the bi-exponential model represents a simplified alternative to multi-exponential T2 analysis. This model has two exponential time constants and a weight fraction W1, which is typically interpreted as the water pool associated with proteoglycan content in the parlance of cartilage multi-exponential T2. Monte Carlo numerical simulations are used to both examine the ability to discriminate between the decays of each model under idealized acquisition conditions, as well as establish accuracy and precision estimates of model fit parameters. These estimates are obtained under both idealized acquisition conditions and acquisition conditions typically encountered with clinical MRI. So for these simulations, signals were generated using each of the models presented above. So the mono-exponential, stretched Mittag-Leffler, stretched exponential, and bi-exponential models. Tissue parameters for each model were derived from experimentally determined measurements in cartilage. And 200 noise realizations were simulated for each condition and each simulated model. As mentioned, 2 acquisition conditions were simulated. The first condition is comparable to our in vitro experimental conditions, which had a very high signal-to-noise ratio and very high frequency sampling of the signal decay. The second condition is more comparable to clinical imaging conditions with more modest signal-to-noise ratio and lower frequency sampling of the decaying signal. In vitro experiments of cartilage explants were used to examine the range of anomalous relaxation parameters for normal and mildly degraded cartilage and for comparison of these parameters with biochemically derived matrix composition. Therefore, cartilage explants were harvested from the septum of young calves and randomly assigned to either control or treatment groups. The treatment groups received an enzymatic degradation using an enzyme chondroitinase AC, which preferentially degrades proteoglycan. Relaxation measurements were made using a 9.4 Tesla vertical bore Bruker DMX, using conditions that produce very high signal-to-noise ratio and very high sampling of the echo decay. Complex phased echo amplitudes were truncated at 2% of the maximum signal for analysis. And samples were then analyzed using the DMMB assay for sulfated glycosaminoglycan content, which is our measure of proteoglycan. The first question we asked with the Monte Carlo simulations is, can we identify the correct model under our in vitro experimental acquisition conditions? Here in Table 1, on the left-hand column, we show the input simulation models, and the fit models are listed across the top here, with mean squared errors listed in the table. This table shows the average mean squared error over each simulation of 200 noise realizations. For the mono-exponential input model, the first row, both the stretch exponential and stretch Mittag-Leffler models fit data equally well. This is because both models reduce the mono-exponential model for an alpha value of 1. The bi-exponential fits a mono-exponential well with the degenerate solution showing 2 components with equal relaxation times. For other input models, smaller mean squared errors were obtained for the correct signal model, with the diagonal of the table showing the lowest mean squared errors. The second question asked with the Monte Carlo simulations is, what are the accuracy and precision of model parameters for discrimination between healthy and diseased tissue? Here, simulations using the in vitro acquisition conditions with high signal-to-noise ratio and high frequency sampling of the relaxation decay show extremely high accuracy and precision for all models. The bi-exponential model precision is the lowest, with a coefficient of variation in W1 and the shortest T2 component of about 2.5%. Results under more modest acquisition conditions show accuracy to within 1% for the mono-exponential and stretched exponential and stretched Mittag-Leffler parameters. The anomalous exponent for both stretched exponential and stretched Mittag-Leffler models show low coefficients of variation, with the stretched Mittag-Leffler showing lower errors than the stretched exponential. errors for W1 in the bioexponential model were substantially larger. This table summarizes results from the biochemical analysis. The DMMB assay showed about a 40% smaller proteoglycan concentration in the enzymatically degraded tissue compared with control tissue, reflecting a modest degradation. This table shows the model parameters obtained from the in vitro experimental data. Monoexponential T2 increased with degradation, consistent with what has previously been shown. T2 values for the stretched exponential and stretched Mittag-Leffler models both increased as well, as did T2 for the bioexponential model. Alpha parameters for the stretched exponential and stretched Mittag-Leffler models significantly increased. Alpha of the stretched exponential model showed greater dynamic range. The apparent decrease in W1 of the bioexponential model was not significant. And the F-test results indicate additional parameters using all three models provided a significant improvement in the fit, and mean squared errors were lowest for the stretched exponential model, indicating the stretched exponential model fit the data best. These figures show correlations between model parameters on the y-axis and biochemically derived proteoglycan content on the x-axis. Monoexponential T2 shows a negative correlation with proteoglycan content as expected. Both alpha of the stretched exponential and stretched Mittag-Leffler models show a negative correlation with the proteoglycan content. The y-intercept of these fits suggests extrapolation of these fits to a monoexponential in the limiting case of complete loss of proteoglycan in the tissue. Alpha of the stretched exponential shows substantially larger dynamic range than alpha of the stretched Mittag-Leffler. Note that the scale of these two plots is the same. The correlation between W1 of the bioexponential model and proteoglycan content shows a small y-intercept and a slope close to 1, suggesting a close correspondence between this bioexponential component fraction and proteoglycan content. This figure shows a representative plot of the residuals from each model fit to relaxation data from control cartilage. The stretch exponential shows substantially smaller residuals compared with the other models. In contrast, the monoexponential and stretch Mittag-Leffler fits show noticeable oscillations about the true signal with deviations on the order of several percent. The residuals from the bioexponential fit are on the order of 1% with similar oscillations to the monoexponential and stretch Mittag-Leffler models. These oscillations in the residuals suggest a non-random source of error. The Wald-Wolfowitz runs test confirm this. Similar errors can be observed in the fit residuals for each of these models to relaxation data from degraded cartilage, though with lower errors. This observation of lower errors for all models is attributed to the larger values of alpha and smaller values of W1 in the degraded samples as compared with control samples. Anomalous T2 decay is often modeled as a sum of individual relaxation times. In a porous gel-like tissue, like cartilage, where water can diffuse through the tissue matrix and experience different microenvironments over the course of the acquisition time, interpretation of pool sizes becomes more complicated. The interpretation of multi-exponential T2 is further complicated by the fact that the numerical inversion for obtaining multiple exponentials is unstable in the presence of noise, posing substantial challenges for clinical applications to cartilage. Even bioexponential fits can be unstable and yield parameters with poor accuracy and precision when challenged with limited SNR, as we've shown with our simulations. The stretched Mittag-Leffler model seeks to incorporate attributes of the tissue environment such as non-local interactions and memory effects microstructural self-similarity, and time scale and length scale invariance. This is accomplished through the definition of the fractional integral, which incorporates the convolution of the power law in time with the evolution of the magnetization over time. The stretched exponential can be motivated by the assumption that the transverse relaxation time constant exhibits a power law time dependence. Stretched exponential can also arise from a fractal generalization of diffusion in space and time. It is also used extensively in non-NMR systems and is shown to arise from non-stationary step lengths in a random walk process. A further interpretation of the stretched exponential model, which also holds for the stretched Mittag-Leffler, is that it represents a compact empirical approximation of an underlying distribution of relaxation times of the system. This is a common interpretation of the stretched exponential model in luminescence decay law. This figure shows the T2 distributions for the stretched exponential function for different values of alpha. Note that as alpha decreases, the distribution becomes more broad and skewed towards more rapidly relaxing T2 values. The stretched Mittag-Leffler model yields a different T2 distribution than this one shown in this figure, but the same general behavior of a more broad distribution with decreasing values of alpha applies. We illustrate this idea in the context of cartilage relaxation. Panel A shows the non-negative least squares derived T2 distribution from control and degraded cartilage samples. Panel B shows the corresponding T2 distribution of the stretched exponential function using model parameter values that best fit the decay data from the corresponding samples in panel A. The T2 distribution for the stretched exponential function in panel B appears as a smooth continuous distribution that resembles the overall envelope of the peaks in panel A. The more rapidly relaxing component fractions here in the non-negative least squares results in panel A have been shown to positively correlate with the concentration of cartilage proteoglycan. Thus, if we extend this interpretation to the correlation between the stretch exponential parameter alpha and proteoglycan, it suggests that alpha captures these rapidly relaxing components modeled as exponentials in the non-negative least squares results, yet with a particularly simplified parameterization. To illustrate the behavior of these model functions, here we show the mono, exponential, stretch Mittag-Leffler, and power functions on a log-log graph, each with the exponent of 0.5. Both the stretch exponential and stretch Mittag-Leffler functions coincide with small arguments of time. With larger arguments of time, the stretch Mittag-Leffler function approaches the power function. We can see this close correspondence between the stretch Mittag-Leffler function and the stretch exponential function at small arguments of time here in panel B. When we fit the stretch Mittag-Leffler model with blue circles here to data modeled using the stretch exponential function represented by these red circles. Despite this correspondence at early times, when the stretch Mittag-Leffler model, again represented by these open blue circles, is fit to data generated using the stretch exponential function over several time scales, the stretch Mittag-Leffler fit deviates from the stretch exponential data at small arguments of time, and thus does not capture well the anomalous features of the decay at early times. Our simulations using the idealized acquisition conditions show the ability to distinguish between each of the four anomalous models through use of the mean squared error, as we show in Table 1. These simulations suggest that fit errors impose a negligible influence on parameter estimates, as we show in Table 2, suggesting our in vitro acquisition conditions were sufficient for examining model parameters as they compare with proteoglycan content. Our simulations using more modest acquisition conditions demonstrate that both The stretch-Mittag-Leffler and stretch exponential models provide accurate and reproducible parameter estimates. Now, when we examine these in the context of cartilage degradation, we see that for a signal-to-noise ratio of 100, our simulations suggest we can estimate the parameter alpha in the stretch exponential model to within 3%. Our in vitro experimental results showed that this parameter alpha for the stretch exponential model changed by about 7% under enzymatic degradation. Now, when we look at the simulation results of the stretch-Mittag-Leffler model, we see that it suggests that we could estimate the parameter alpha to within about 1.3% of its true value. However, our in vitro experimental results show that this parameter alpha for the stretch-Mittag-Leffler model only changed by about 1.3% with degradation, suggesting that this model under these acquisition conditions would not be able to distinguish between normal and degraded tissue. The bioexponential model showed high bias and dispersion under these modest acquisition conditions, with an accuracy and precision for W1 of greater than 25% and 35%. And to compare this with the changes we observed in our in vitro experiment, degradation decreased W1 by about 27%. Using the relaxation data from our in vitro experiments with high signal to noise and high frequency echo sampling, we closely examined the misfit from each of the models during early, intermediate, and late times over the decay period. The residuals of the mono-exponential model showed large oscillations during early, intermediate, and late times. The residuals for the stretch-Mittag-Leffler model showed deviations at early and intermediate times similar to the mono-exponential fit, but show a smaller deviation at later times owing to its heavy tail characteristics. The residuals of the bioexponential model show a similar pattern to the mono-exponential and stretch-Mittag-Leffler models, though with substantially smaller deviations of within 1% of the signal. And the residuals from the stretch exponential model, in contrast, show substantially smaller deviations over the entire decay of the signal. In conclusion, we suggest that the stretch exponential, stretch-Mittag-Leffler, and bioexponential models provide alternative and physically plausible models for T2 relaxation. The stretching parameter alpha reflects microstructural complexity of the matrix, and the short T2 component W1 is interpreted as reflecting proteoglycan-associated water. This holds when its T2 is on the order of 10 to 20 milliseconds. The stretch exponential model more accurately describes transverse relaxation data over the entire acquisition time. This is supported by lower mean squared error and the F-test. The stretch exponential model yields parameter estimates with sufficient accuracy and precision for detecting modest depletion of proteoglycan content in cartilage under limited signal-to-noise ratio and echo sampling rate. And alpha from the stretch exponential model correlates well with proteoglycan content. Thus, the stretch exponential model shows potential for providing a clinical marker of cartilage matrix integrity.